Hi there, I found this vintage DATRON 1030A AC True RMS meter on eBay with the seller claiming it's an attic find and unable to test. This is an AC only True RMS meter that goes from 1000 volts down to 10 millivolts and can handle frequencies of up to 1 MHz. You may not have heard of DATRON. Well, DATRON was a UK company that made electronic measuring and testing equipment from 1979 to 1992. Then they became WaveTech, and since 2000 they are now part of Fluke. It looks a bit dusty now, but this meter is in absolutely mint condition. There are no cull stickers, and I'm pretty sure this was never opened since it left the factory. I put it on the bench, opened it up to give it a test. This is a video of that first test. Well, it does not blow up, and so far no magic smoke, but not much is happening. In such cases, it's always the first step to check the power rails. Apologies, I accidentally covered most of the over and at the back with my hand, but you can just make out 14.5 volts and minus 14.7 volts. Plus minus 15 volts is normal, and these are a bit low. As it's common, the digital part is isolated from the analog part and has its own power supply. 5 volts, just as it should be. Pressing the range keys moves the decimal point, which is not much, but at least something. By chance I tried the highest range and now it does show something, but considering this is the 1000 volt range, the numbers make no sense and are all over the place. If I select any other range, it's just a blank display. The 1030A has two PCBs. The meter is standing on its side in this shot, and what you see is the upper PCB containing the power supply and the analog to digital conversion and display. Just now, when I measured the plus minus 15 volts, I was probing these 15 volts regulators here. On the left are two 1000 microfarad smoothing caps for these rails. The 5 volt regulator sits on this piece of metal as a heatsink. Immediately below is the full bridge rectifier for the 5 volt rail, and the big yellow cap of 4700 microfarads also belongs to that circuit. The analog front end is on the second PCB underneath. On the left is the long row of range and other buttons. This PCB contains some interesting things. Prominently, there's a special DATRON chip. The schematic just shows it as a box. I believe it's actually one of those 5 transistors in a single substrate type of chips, like the CA3083, but hand selected by DATRON for its specs. The special selection applies to a lot of things. Lots of resistors on standoffs that are obviously soldered in afterwards as part of calibration. It gives the board an untidy prototype kind of look. The dual FETs in this case, with a solder blob on top, are also specially chosen and match the ones in the adjacent one. As part of the manufacturing, they are measured and some resistors are selected based on the result. As part of this selection process, one of the dual FET cases is heated with a soldering iron, hence the blob on top. There are a lot of interesting solutions like this thermally coupled transistors, or this one bending over but not quite touching the op-amp underneath. On the bottom are two relays. One switches in additional attenuation for high voltage ranges, while the other bridges or enables that big yellow cap next to it to switch between DC and AC coupled. Soon after I took the video of the first power up, the meter stopped working even in the 1000 volt range, and I noticed there was no more relay clicking when I pressed the AC-DC switch. One end of the relay coils are hanging on the plus 15 volt rail, and the relays are activated by transistors pulling the other end of the coil to the minus 15 volt rail. If the relays no longer work, something must have killed either one or both rails within a few minutes of operating, although no magic smoke had made an appearance. In such cases, I have learned to look for capacitors, especially tantalum types that hang between power rails and ground, like for example C20 here. If that one failed short, it would pull the plus 15 volt rail to ground. Since I measured that the minus 15 volts was gone, I looked for caps between the negative rail to ground, and that turned out to be C19. For a quick test I snipped off one of its legs and the meter was working again. The regulator in the power supply had limited the current, so nothing blew up. There are 4 tantalum caps on this board and more on the AD board above. Incidentally, the failed C20 is the one at the very bottom here. I had so many vintage tantalum caps failing on me that I decided to replace each and every one of them and use electrolytic caps instead. At the same time, I decided to replace the electrolytic caps in the power supply just for good measure. But before that, there's an interesting thing. I noticed my board had serial number 6. Wow! After talking with other DATRON 1030A owners, it turns out I must have really one of the very first ones ever made. I reckon it must be around 1985, judging from the date codes on the chips. On the left is my unit and on the right the same view on a later 1030A. There are some changes in the PCBs, and also the later 1030A is in a much bigger enclosure. Look at all the space there is on the rear. Also, the tantalum caps are of a different brand and all blue on this board. Anyway, whatever color, out with them on my board. Apart from the busted one, I did not find any capacitors that were really bad or close to fail. Seems at least the tantalums work fine 1 minute and then fail suddenly and unpredictably. I feel better that they're all out. This is the topside AD board with my new blue electrolytic caps and all the small red electrolytic caps replacing tantalum ones. At this stage I was still waiting to receive the replacement for the large 4700 microfarad smoothing cap. And all tantalum caps replaced on the RMS board as well. Although I did not find any significant problems with the removed capacitors, it had a big impact because the meter now behaves much better and displays sensible values. I am feeding it with just above 1 volt RMS at 1 kHz and the DATRON is not far off. 100 millivolts now, and again it may be a little off, but actually I forgot to change the BM869S to millivolts as well, so the DATRON may in fact be right. 10 millivolts now, and the DATRON is again not far. It needs a bit of calibration, but it's quite usable already. So far so good, but there's more. You may have noticed that the PCB has a few unpopulated locations close to the display. And removing the front panel reveals that the display PCB is in fact prepared for a 5th digit. I then noticed that in later 1030As and in the service manual, the display is very different from mine. They use neon-filled Panaplex types that consist of a 2-digit tube next to a 3-digit tube element, in total 5 digits. In fact, in later 1030As, DATRON already solders in the sockets and populates them with the required ICs during the factory test, only to pull the ICs needed for the 5th digit back out later if you did not order the special 5-digit version. Of course, Panaplex drivers are different from what I have here. In my case, I have to find a 7-segment display that matches the other 4, populate the segment driver resistors, and add the 7-segment decoder and latch chips. Finding the exact same 7-segment display was easy enough. It's an HP part number 5082-7730, 7.6 mm by 10.9 or 0.3 by 0.43 inch common anode display with left-hand decimal point. I did not have the fancy sockets that DATRON uses, but my solution works well enough. Soldering in the 2 missing sockets on the AD PCB was just 5 minutes work. After putting the ICs in, it worked immediately. I now have a 5-digit DATRON 1030A for less than £5 extra cost. I already had the sockets, resistors, and the missing 7447 BCD to 7-segment decoder and the 7475 4-bit latch from eBay were just pennies. The 7-segment display was the most expensive since I wanted a genuine new old stock part to match the look and brightness of the other 4. The 1030A display is not multiplexed, and maybe that's not needed using neon Panaplex tubes, but with the standard 7-segment LEDs, the current draw is highly dependent on how many segments are lit. Worst case, each digit showing the number 8 with a decimal point draws 100 milliamps. The unit has no ventilation and it was already running very hot. The new digit definitely added to the problem and it gets far too hot for my liking. I can hardly touch my new installed smoothing cap in the 5V section after running it for 15 minutes with the lid closed. This is a problem for part 2 of the video, so stay tuned for an update. If you like my video, don't forget to subscribe if you not have already, and maybe consider becoming a Patreon. That would really help this channel. The link is in the description. As Patreon, you always get early access to videos, a blog and other exclusive content. Thanks for watching.